is lecture video 36, and we will cover indefinite integrals and substitution method in this lecture. So what is an indefinite integral, or what is the difference between a definite integral or indefinite integral? So let's cover this first. If you put upper-lower boundaries for your integral like this, then this will be an definite integral. Let's assume that big letter f is the antiderivative of small letter f function. Antiderivative. Okay, so if you take the derivative of big letter f function, you will again find your f of x function. So derivative and antiderivative are inverse operations, and taking antiderivative is in fact the same as taking integral. From now on, we will be using the integral word for taking the antiderivative. This is a definite integral, okay? What we call as the indefinite integral is the one without upper-lower bounds. Okay, this time you are still taking the integral of your function, but you are not putting upper-lower bounds. So you just put f of x dx, and the result is the antiderivative of it. But this time, by the way, you have to evaluate this antiderivative function from a to b, of course. So it will be like this. So the result of the definite integral is a number. Don't forget this. You will find a number as the result of your definite integral, which is the antiderivative function evaluated at upper-lower bounds like this, so it becomes a number. But for the indefinite case, indefinite integral, there is no upper-lower bound, so you just put the antiderivative function, but here you need to put an arbitrary constant, because if you derive this whole thing, the constant will gone. So that's why the derivative of this whole expression is still small letter f function. So the result of the indefinite integral is antiderivative of the function plus an arbitrary constant c. Okay, after recalling this difference between a definite integral and indefinite integral, now we can look at substitution method. Okay, this method gives us a way to integrate more complicated functions like this. For example, we no longer have just f of x dx, but more complicated expression. So applying substitution means that you choose some part of your integral as your u, and then you try to express the integral in terms of u and du. So if u is g of x, then this part is the differential of u, right? Okay, what I wrote there is, if you choose u as g of x, then du is g prime x dx. We covered differentials in one of the previous lectures. So then this integral can be rewritten as f of u du. And then you can find the result of this integral because it is in a more simpler form. So if you know the antiderivative function of your f of u, then the result will be something like this, where big letter f is the antiderivative of this small letter f function. Okay, instead of writing antiderivatives anymore, it is the integral of this letter f function. We can use the word integral from now on. Okay, let's apply substitution method over these examples now. Okay, substitution is already given in the first example. Let's choose u as 2x squared. Then what you should do is to compute du as this one. And then your aim is to rewrite your function in terms of u's and du's. You need to get rid of all the excess, okay? And this part you already express it as u, so sine u. And can you express x dx in terms of du? It is possible because from this line you see that du x dx is what is exactly du over 4. Okay, So this part is in fact du over 4. So you have an integral like this now, sine u du, and you know how to integrate sine function. Tell me a function, by the way, this is not 2 but 4. Tell me a function now whose derivative is sine u. Is there such a function? Yes. It must be minus cosine u, right? If you derivate minus cosine u, you will find sine u. 1 over 4 was there. And since this is an indefinite integral, no boundary, see? You have to put this arbitrary constant c at the end. And then look at your function. You get your example. Your example was in terms of x, but you find the result in terms of u. You shouldn't leave the result like this. You should do back substitution, meaning that you should turn back to your original variable x by putting 2x squared for you. Okay? And this arbitrary constant should be there because it is an indefinite integral. Okay? So this is how you apply substitutions by taking integrals. Okay, let me put here substitution. Okay, let's look at the second example. Here we have secant times tangent example, and substitution is already given as u equals 2t. Then du is, take the derivative with respect to t, 2 times dt. So this is already chosen as u, this is already chosen as u, and dt is what? From here, it is possible to express dt in terms of du. It is in fact du over 2. So it is possible to rewrite your function in terms of u's and du's. So what is it? Secant u times tangent u in terms of, instead of dt, you write du over 2. So it is 1 over, okay, let me write this again, secant u, tangent u, du. So 1 over, tell me a function whose derivative is secant times tangent. It is obviously secant u. Don't forget to put this arbitrary constant c. And now you have to turn back to your original variable t. So the result is, okay. So let me write the result over this line. 1 over 2 secant u is 2t plus c. Okay, let's move on with the next example. Okay, so the substitution is not given here. We need to choose a substitution. Always you will choose some part from your question. Either this part you can choose as u or this part as u. You will see by doing trials and errors, you will understand which choice of u is working. Okay, let's try this one first. So I choose this as my substitution. U is 1 minus cosine t over 2. Then what is du? Take the derivative. Derivative of cosine is minus sine. Another minus is here. So it is sine t over 2. And then you need to multiply with the derivative of the insider part. Always put dt. So this integral can be rewritten in terms of u's and du's. This part is already chosen as u, so u square. What about this part? So you see it here, right? Sine t over 2 dt is in fact 2 times du. So 2 times du for this part, and then it becomes simple to integrate this function because this is integral of u square du. What is integral of u square? Add 1 to the power, divide by the same power. Since this is an indefinite integral, I put my arbitrary constant c. And as the last line, I do back substitution. I need to turn back to my original variable t. So u was this thing. Just write it for you. Cube over 3 plus this arbitrary constant, okay? So instead of u, you insert its expression in terms of t. Okay, next example. So we need to choose a working substitution here. substitution should be, you should either choose this part as u or this part as u, and it always makes more sense to choose someone from the nominator as u, not to deal with the denominator of the quotients. So let's try this one. We will see after we write it if it works or not. So what is the u then? Derivative of the square root function is 1 over 2 times itself times dx, of course. So let's see if it is possible to write everything here in terms of u's and du's. So what is square root of x okay, you see this part here, right? And it appeared here. So dx over square root of x is in fact 2 times du, as you can see from this line. So the integral can be rewritten as u to the power 1 over 3 times 2 times du. You see, 2 times du is dx over square root of x. So you see, this substitution transformed our integral to a very simple one. It is 2 times u to the power 1/3 du, and we know how to integrate power functions. Add 1 to the power, divide by the same power then. Okay, so we will add 1 to the power and then I divide by the same power. 1 over 3 plus 1, 1 over 3 plus 1. Don't forget to put this arbitrary constant c. Okay, and then we need to do some back substitution to turn back our original variable x. So what we have here is 4 over 3 plus c, but now I am doing back substitution in terms of u. I am turning back the original variable x. Okay, this is the result. And everywhere you don't forget to put this arbitrary constant c's because you are taking indefinite integrals. Okay, let's move on with the next example. We need to choose a nice substitution. Let's choose this part as u and try to see what happens. U is 5s plus 4, then du is 5ds, right? 5ds. And then let's see if it is possible to rewrite your integral in terms of u's and du's only. This part is already chosen as square root of u. What is ds in terms of du? ds is in fact du over 5. Okay, du over 5 is what ds is. So your integral looks like this now, which we can handle, right? Du over square root u. This is 1 over 5 integral of, what is this? This is u to the power 1 over 2. And if you write it as a power function, you need to put minus sign because you are taking it to the denominator, du. And then once you see it as a power function like this, you can easily integrate it because all you need to do is add 1 to the power, divide by the same power. Don't forget to put this arbitrary constant c, and then the result is, so to the power 1 over 2 plus c. Now I am doing back substitution. U was 5s plus 4. Okay, so like this. Okay, and maybe you can write one more line for this example. Then the result is 2 over 5. This over 1 over 2 means square root of that expression. Okay, plus c, so 5s plus 4. Okay, this is your final result. Okay, next example about how we use substitutions to evaluate indefinite integrals. Okay, so, this function seems a bit complicated, but no matter how complicated it is, substitution may transform it to a simple example. So we will choose a substitution. For example, maybe we can try u equals sine, okay. Either you will choose this part as u or sine square root theta as u. If you choose u equals cosine, from its derivative, you will never get 1 over sine kind of things. That's why it makes more sense to choose this denominator as your u, like sine square root theta. Let's see what happens if you choose this one. The derivative of sine is cosine, and then I will multiply with the derivative of the insider function like this, and put d theta there. You see, this is perfectly working very nicely, as I already called this part as u, so it is u squared, sine squared of this thing is u squared, and what you see here is cosine square root theta over 2 times square root theta d theta. I mean, this whole thing, this whole thing is already written here, you see? It is the same. That's why this part can be written as 2 times du. To just send 2 to the right-hand side, okay? So it can be written as 2 times du. So 2 du, I will just write there. Okay, now this is a very simple function to integrate because it is just a power function like this. So add 1 to the power, divide by the same power, your arbitrary constant. So it is minus 2 over u plus c, and then you need to do back substitution. So minus 2 over what was u? U was this thing. Sine square root theta was u, and then plus c, of course. So this is your overall result now. Instead of u, you do back substitution. Okay, this is how substitution method works for the integrals. You choose some part of your function as your u, and then you try to express what remains as du. So your aim is to rewrite your function in terms of u's and du's only. You need to get rid of all the old variables. New integrals should be in terms of u's and du's, and then with this simple integral you can deal with. So let's move on. Now we will talk about integrals of sine square and cosine square x. So these are the half angle formulas for cosine square and sine square x, and integrating sine square and cosine square is possible only if you use these half angle formulas. And if you compare these two formulas, the only difference is this sign, right? In sine you have minus, in cosine square you have plus. This is the only difference. And there is one more thing to be emphasized here. Why we are calling them half angle formulas? Because you have here x, but on the right hand side you double the angle, 2x. So that's why these formulas are called half angle formulas. So let's integrate sine square, for example. So the only way to integrate sine square dx is to use this formula. Okay, instead of sine square x, I put this trigonometric identity, then I will take 1/2 out from the integral because it is just a constant multiple, and then I can integrate this easily. What is the integral of 1 with respect to x? So it is just x. What is the integration of cosine 2x? So tell me a function whose derivative is cosine 2x. It is sine 2x over 2, right? And then you will put your arbitrary constant here. By the way, maybe I can put here a recall about the integrals of sine kx and cosine kx. So sine kx is... So you will consider the antiderivative of it. So you will try to find a function here whose derivative is sine kx. So it is the cosine kx function. But if you derive cosine kx, you will, if you take the derivative of it, okay, it is sine kx, but times k. You have to multiply with k. To get rid of that k, you have to divide by it. Let's put this arbitrary constant here. And it is similarly for cosine kx. It is sine kx over k plus c. That's why we put here sine 2x over 2. So you need to divide by the constant coefficient there. This is the result of the integral sine square x. And similarly, cosine square x is also integrated by using this trigonometric formula. So 1/2 goes out, 1 plus cosine 2x dx, it is 1/2. Integral of 1 is just x. Integral of cosine 2x is sine 2x over 2. And then plus this arbitrary constant. So these trigonometric formulas for sine square x and cosine square x are very useful because you need them to integrate sine square and cosine square x function. So I stop here. Thank you for your attention.